Hi. In a previous video, we saw that the k-means algorithm fails when the dimension of the data becomes too high. In this video, I'm going to tell you about high dimension in general and give you some idea that in high dimensions, our intuition really fails us. It's hard to understand what is exactly going on, and in order to understand, what you really need to use is the law of large numbers and central limit theorem rather than your intuition about 2 and 3 dimensions. Okay. So throughout this notebook, we're going to use a very simple distribution. Basically, we're going to have a center at 5 and a center at -5. And both of these centers are, you can think about them as balls, and their radius is 1. So in 2 dimensions, or even in 3 dimensions, these seem very well separated things. But as we'll see, when the dimension becomes higher and higher, it becomes harder and harder to separate these two things, or to see that basically anything special is happening in dimension number 1. So the first thing we're looking here at is the length of the vector. Okay, so if the vectors are at -5 and 5, then we expect a length of about 5. Okay, so that's right. But when we go into higher dimension, the length increases. Why does it increase? It increases because we have these other dimensions that have contributions. And as we go to higher and higher dimensions, finally to dimension 2000, we see that the distribution is extremely concentrated around, in this case, something like 45. Okay, so 45 is the length of the vector regardless of where it comes. And you can see that the distance of 5 between or 10 between the two centers is not really the important thing. The fact that the center itself is at 5 or -5 is not really the important thing. The important thing is the high dimensional contributions. Okay, so basically all vectors in this case have the same length. So next, let's think about the distance between 2 points chosen at random. As I said before, we have these two centers, one at -5 and one at 5. And so the distance between 2 points will basically depend on whether they come from the same cluster or whether they come from the other cluster. Okay, so we expect to see distances close to 0 in one case and close to 10 in the other case. However, when the dimension increases, the distance between the points will become dominated by the other dimension when there is no separation between the two clusters. And so at very high dimension, the distance between the 2 points at the same cluster is exactly the same as the distance between points in different clusters, which is very counterintuitive. But if you think about all the contributions of the other dimensions, you realize that this one dimension that we have has a negligible effect on the distance. So here's how it looks. In 2 dimension, we have a very clear separation. Here are the distances between things in the same cluster, and here are the distance between things in 2 different clusters. In dimension 20, these two clusters start to merge. Okay, so it's harder a little bit to separate between what is a distance within cluster and between clusters. When you get to 200, it becomes completely impossible to separate. And when you get to 2000, it really is just a very highly concentrated peak at one particular distance, which would be the distance. So the distance between any 2 points is about 65, regardless of whether they come from the same cluster or a different cluster. And if you think about it, that obviously makes it impossible for k-means to do its job, because the distances are essentially all the same. Dot products we're going to look at also. So let's say that we take a dot product between the 2 vectors that we have. So in this case, if they come from separate clusters, we get 5 times -5 approximately, so -25. And if they come from the same one, we'll get +25. Okay, but again, as the dimension increases, this effect of minus 25 to plus 25 is still there, but it gets completely absorbed inside the noise. So this is what we see. Basically, in 2 dimensions, we have a very nice separation. Even in 20 dimensions, we have a pretty nice separation. In 200 dimensions, the separation is starting to go away. And when we look at dimension 2000, there is really no separation. It's not that the distances is not minus 5 to plus 25, but there is other effects which are from the other dimensions which cause the majority of the effect. So to summarize, if we use our 2D or 3D intuitions in high dimensions, things break down. Basically, things are not the way that we can think about them in 2 or 3 dimensions. Basically, any 2 points have the same distance. Any 2 vectors have a dot product of 0, and so on. This is sometimes called in statistics the curse of dimensionality, because most statistical methods break down when you have high dimensions. So I hope that you'll remember that lesson. It's a general thing that holds in many, many contexts. And I will see you the next time. See you then.